simply because it's really hard to do. This is the second question, the stats paper. And the problem isn't to do with the maths, it's to do with where I can write. So anyway, this is a partially completed box plot for figure 1, and it shows the distribution of the daily mean air temperatures using the data from a large data set for Beijing in 2015. I don't have that data set. An outlier is defined as 1.5 times the interquartile range below Q1 or 1.5 times IQR above Q3. The three lowest air temperatures are 7.6, 8.1 and 9.1 centigrade, and the highest is 32.5. Complete the box plot in figure 1 showing clearly any outliers. So let's just find out. So this is 26. Let's find the interquartile range first. So 26.6 minus, that looks like 19.4. That equals 7.2. So the 1.5 times 7.2 equals, hang on, let's try going off the thing I was just doing, and so that's 1.5 times 7.2 equals 10.8. So 10.8, we're going to go 19.4 minus 10.8. Well, that would be 19.4 minus 10.8. I've just given myself a ridiculous answer, that's why. Equals 8.6. So we know that this one and this one are outside that, whereas 9.1 isn't. So let's make 9.1 our lowest. That would be our... And then we can put that there. I'm not drawing that well. And then 7.6 and 8.1 can go here and here, because they're outside of that. And then let's add 10.8 to 26.6. Well, it goes way beyond that anyway, and so we won't worry about that. And 32.5 can be our last one, which is there. And then let's just put that in there. So that's our lowest point without being outside or being an outlier, and the upper point would be something around 20. Anyway, it would be above 34, so it doesn't go on there. Using your knowledge of the large data set, suggest which months the two outliers are likely to come from. I don't know, but this is Beijing. Beijing gets really cold, so it's going to be much, much colder than that in the winter. But that's not really maths, is it? Using data from the data set, Simon produced the following summary statistics. So so the amount of days, that's the sum of all the temperatures, and that's the sum of all the temperatures. Anyway, show that to three significant figures, the standard deviation is 5.19 degrees centigrade. So you do the square root of this, which is 4952.906 over 184, and that gives us square root, pop in the thing that makes it look like that. Wow, that 4 looks like a 9, doesn't it? 4952.906 over 184. And that equals 5.188, which equals to 3 sig figs 1.9. There we go. Right, Simon decides to model the air temperatures with a random variable, so a normal distribution. Using Simon's model, calculate the 10th and the 90th interpercentile range. So what you do for this is you go to your distribution, and then you go to inverse distribution, inverse normal. Okay, now 10th, that would be a 0.1 in terms of area, so you do 0.1. Then the mu, or this, so this is area equals that, mu equals your 5.19, and then your other thing equals, then your mean equals 22.6. So if you put those in, and then equals, and then 22.6. So the chances of it being 10th, there being in the 10th percentile is, so 10th equals 15.9487. Now then for the area, for the 90th, you put in 0.9. So go back, go equals, go inverse normal, and put in 0.9, and then that will give you 29. So the 90th equals 29.251,253. And now just go back to your normal settings and do one, take one away from the other. I'm just going to see if answer minus 15.9487 equals, yeah, that seems right. So the answer equals 13.3, and that seems quite reasonable. State two variables from the large data set that are not suitable to be modelled by normal distribution, given an answer, reason for each answer. Well, it's anything that's not modelled by a bell curve by normal distribution. So if it's to do with weather, I don't know, wind, sun is kind of like that. Tornadoes, you never know when they're coming. They're not normal, are they? So that might be anything like that.